All right, let's continue the same chapter, chapter 3. In previous class, we started with the introduction of the standard air and the moisture, and we saw that various fundamental parameter of the moisture can be computed with the help of various empirical relations, as well as we can also use the psychometric chart for calculating the same fundamental parameter. Now, the psychometric chart basically give you an approximation. I mean, some of the data that may not be exactly, I mean, pointed out on the psychometric chart. For example, let's say if I ask you to figure out the properties of the moisture, let's say at 49% relative humidity. So that means there is no line of 49% relative humidity. So you have to make certain interpolation between the 50% and the 60%. But if you use the empirical relationship for calculating the same property, that can be computed uh, relatively more accurate value. Anyhow, the psychometric chart basically give you a quick way of determining the fundamental properties. And we also discussed that the air conditioning processes, we discussed the simple heating, simple cooling, and humidification process. So we'll continue. This was the simple heating and simple cooling process. And then we discussed the bypass factor and the efficiency of the heating and cooling coil. And then we discuss humidification and dehumidification process. So we'll continue. The next air conditioning process is heating and humidification. Now, where is the application of the heating and humidification process? I mean, when you heat air, moisture, as well as humidify air, you can have this application nowadays in winter. I mean, you heat the moisture as well as you humidify that. Or the same application can be figured out in case of cooling tower. You know that the moisture enter in a cooling tower from the bottom, and from the top you spray water. So as a result, the air leaving the cooling tower is hotter. It has taken the heat of the hot water as well as it is much humidified. So these two applications can be associated with the heating and humidification process. Now, this heating and humidification process can be accomplished separately, or it can take place simultaneously as well. As you can see in the figure, the process, let's say from 1 to 2, is with the help of a heating coil. This heating coil can be operated with steam, or it can be electric coil. So the moisture at point 1, when it come contact with the heating coil, this is just simple heating. That means only the dry bulb temperature of the moisture is increasing, right? And then subsequently, when the dry air is sprayed with the help of some humidifier, then you are adding the humidity. You are increasing the humidity of or the water content of the moisture. So in this figure, this is accomplished separately. I mean, from 1 to 2, you are heating, and then from 2 to 3, you are humidifying. But this heating and humidification process may take place simultaneously. For example, let's say instead of the water, I mean, we assume that the sprayed water is at the same temperature at the temperature of is at point 2. But sometimes this spray water, instead of spray water, you can be used as a let's say steam vapor. So steam vapor mean they are at a high temperature. So that means you are heating as well as you are increasing the moisture content. So the heating and humidification process can take simultaneously as well. This process can be drawn on the psychometric chart as well. As you can see in the psychometric chart, from 1 to 2 is a simple heating process. This horizontal line is a simple the heating process from 1 to 2, whereas from 2 to 3 is a heating as well as a humidification process. And this is heating as well as the humidification process. What about the mass and energy balance? Let's say for the dry air first. For the dry air, whatever is the mass of the dry air at, let's say, point 1, let's say MA1 dot, that is equal to MA2 is equal to MA3. So the mass of the dry air is not changing throughout. Right? What about the mass of the water vapors? As you can see, the mass of the water vapors is related with the omega value, right? So that means omega 1 is equal to omega 2. So there is no change of the water contents from point 1 to point 2, right? So that's simple heating process. However, when the humidifier is there, then from 2 to 3, you are adding the water vapors. Now, what is the value of that water vapors? That is basically, I mean, what is the value of that water vapor that you have added? This is omega 3, right? So that means this is equal to omega 3 minus omega 2 into MA. MA is the mass of the dry air. So the amount of the water vapors MW that you added as a result of the humidifier, that is equal to the difference of the omega 3 and omega 2, right? Omega 3 minus omega 2 multiplied by the mass of the dry air. So this is how you can calculate, but this formula is again derived from the energy balance as I discussed in the previous class, right? That means the mass of the dry air remains same. Whatever is Ma1 is equal to Ma2 is equal to Ma3 even. So that means this is not varying. However, mass balance for the water, as you can see, there is no change in the mass water from 1 to 2. However, from 2 to 3, there is a change. So you have to make an energy balance. So that means Ma1 omega 1, right? In that case is equal to, I mean, for 1 to 2, this is equal. As you can see, there is no change from 1 to 2. However, there is a change between 2 to 3. So you have to again introduce a new energy balance between 2 and 3. So between 2 and 3 mean that omega 2 into Ma plus the MW, that should be equal to omega 3 into Ma3. So yeah, you can see here. So this term will go on the other hand side. So it will be the Ma2 is equal to Ma3. So that will be common. So that means omega 3 minus omega. I mean, you can get MAW is equal to MA dot omega 3 minus omega 1. So the same value. So basically that we have derived from the energy balance. Similarly, from the mass balance of the water vapors. Similarly, we can draw from the energy balance. You can see the energy balance between, let's say, 1 and 2, right? Energy balance between 1 and 2. So here we are just adding the sensible heat only. As you can see, we are just adding from 1 to 2, we are just adding sensible heat. So sensible heat we can calculate by the difference of the enthalpy, right? If we can locate the 2 point 1 and 2, that means we know the H2 and H1. So the sensible heat added between 1 and 2, that's the difference of the enthalpy. That means H2 minus H1 is equal to the sensible heat added. If you know the mass of the dry air, then you can multiply Ma dot. So that will give you the total sensible heat that is added as a result of the heating coil. Whereas from 2 to 3, you are adding sensible heat as well as you are adding the latent heat. I mean, from 2 to 3, the process from 2 to 3, the total heat added between 2 to 3 is again the difference of H3 minus H2. But this total heat is a sum of this is the sensible heat, because sensible heat mean that's as a result of the temperature difference. Let's say this is T3, right? This is T2. So as a result of the temperature difference, right? This is the sensible heat, and then this is constant temperature. That's called the latent heat. So this part from two horizontal part, let's say this point is, let's say A, the point between 2 and A is a sensible heat, then from A to 3 is a latent heat. So the total heat from 2 to 3 is the sum of the sensible heat from A to 2 to A, and A to 3 is the latent heat. So the total heat is equal to the sum of the sensible heat and the latent heat. Then since as I showed you in the previous slide, there is, the total heat is basically the sum of the sensible heat and the latent heat. Now there is a factor we call the sensible heat factor. This sensible heat factor is basically a representation of the fraction of the sensible heat that is added from the part of the total heat supplied. So you can say basically this is the ratio of the sensible heat to the total heat That's called the sensible heat factor. And mathematically, the SHF or the sensible heat factor is the ratio of the sensible heat to the total heat. So since the total heat is basically the sensible heat plus latent heat. So this is basically, this give you that out of the total heat, how much is the sensible heat supplied to get the required condition of the moist air. As you can see from the psychometric chart, even I explained in the previous lecture as well, that if there is any process, let's say there is a process 1 to 2. So this process 1 to 2 is basically the heating and humidification process. I mean, you are heating as well as you are humidify. So this process, I mean, if you draw a parallel line, you can see there is a D shape. This D shape on which the sensible heat factor is located. So you can locate the exactly parallel line, parallel to this line. I mean, from 1 to 2, if you draw a parallel line, as you can see the parallel line of this line, then it cuts here. So the point where it cuts, that is the sensible heat factor. So that means directly you can see that the how much is the portion of the sensible heat for this heating and humidification process. So from 1 to 2, you draw a parallel line on that shape. So this will give you the value of the sensible heat factor. So in this shape, you can see the sensible heat factor is approximately 0.8. Right, and let's say the same process can be, I mean, during the cooling process as well. Let's say there is a cooling process with the help of a cooling coil, and the point 4 is the ADP, apparatus dew point. So when the moisture come in contact with the cooling coil, so its temperature is dropped as well as dehumidified. So you can see the total heat removed from 1 to 2 is basically the total heat, which is equal to H1 minus H2. But this total heat is basically the sum of the this is the latent heat and this is the sensible heat. That means H1 plus HA, sorry, H1 minus, sorry, this is H1 minus HA plus, this is the latent part and this is the sensible part. That means HA minus H2. So basically this is again equal to H1 minus H2, right? So this is basically equivalent. So the total heat supplied is the sum of the latent heat plus the sensible heat. You can see here. So same value we can, I mean, we can get that value if we draw a line parallel to this one. This will give you the value of the sensible heat factor. Now the sensible heat factor can be positive, it can be negative, right? As you can see, the sensible heat values are negative. That depends on the value of the denominator. Let's say if the value is negative, then you will get the sensible heat factor to be negative. I mean, let's say because sometimes in case of the heat removal process, it can be negative. Like if you draw a parallel line to this one, let's say this one, right, and you try to draw a parallel line on the D, then you will get a negative line. And this process is called humidification, cooling and humidification process. This is just like the process in an air conditioner. This is a summer air conditioning process, right? So this is the basically the sensible heat factor of this shape. Let me erase this. So as you can see, the sensible heat factor is basically the sensible heat divided by the total heat. So the sensible heat is this one. I mean, sensible heat is between A and 2. So HA minus H2, whereas the total heat is H1 minus H2. And then the next air conditioning process is cooling and dehumidification process. Right, this is typical application of the summer air conditioning. You know that in our domestic air conditioner, they cool as well as dehumidified because the surface temperature of the coil is lower than the dew point temperature of the incoming air. So when the incoming air or the room air, when it come in contact with the cooling coil of that evaporator, then it cool down as well as the water vapors, it condense into vapors. So that's called the cooling and dehumidification process. As you can see in this figure, that the outside air at point 1, I mean, this is the outside air which is hot and humid, right? Which is hot and humid. So when the outside air, which is during the summer, which is hot and humid, when it come in contact with the cooling coil in which the refrigerant, which is also called the evaporative coil, in which the refrigerant is moving inside the coil, when that hot air come in contact with that cooling coil, then what happens? If the surface temperature of the cooling coil is lower than the dew point temperature of the incoming air, then not only the outside air is cooled down, I mean the temperature is dropped, but also the humidity is dropped, because the water vapors present inside the air, they are condensed. So that condense can be removed outside. Normally this part we call the is located outside, where the condensate is collected. Now the cooling and dehumidification process can also be drawn on the psychrometric chart. Like the outside air is humid, its humidity is high, let's say omega 1, and let's say the dry bulb temperature is TD1, let's say TD1, right? Dry bulb temperature as state 1. So when it come in contact with the cooling coil, then its dry bulb temperature is reduced, as well as the humidity is reduced. So how can we figure out that how much heat is removed, right? How much heat is removed by the refrigerant coil from the outside air, and how much water is condensed as a result of that cooling process. So this will use the same concept. I mean, we have to adopt the mass and energy balance. For example, the mass of the dry air, it remains constant. Whatever is the mass Ma1 at this point 1 is equal to Ma2. What about the mass of the water vapors? Mass of the water vapors, as you know, for example, here mass of the water vapors is basically the difference. Mw is basically the difference of the omega. I mean omega 1 minus omega 2 into M dot A. So this is basically as a result of the energy balance for the water vapors, because water vapors, I mean, we can apply the water vapors balance for the water vapors and the dry air and the energy balance. For example, the first equation is the uh, dry air mass balance. So there is no change of the dry air. Ma1, Ma2 is equal to Ma1. What about the water vapors? Here the water vapors is Ma1 into omega 1, right? And this is the incoming, this is the in. And where are the out water vapors? Here is the out water vapors, and here is the out. So incoming should be equal to outgoing. So in is equal to out. So out is at this location, I mean Ma2 omega 2 and Mw. So this Mw, mass of the water vapors, is basically the difference of the humidity ratio omega 1 minus omega 2 into the mass of the dry air. So now similarly for the energy balance, what is the energy going in and what is the energy going out? So energy in is just the energy of this moist air, right? Energy of the moist air is the energy in, whereas where the energy going, one of the energy going is here, enthalpy. I mean, this is H1, let's say, I mean, Ma1, H1. So the energy here going is Ma H2, right? So the heat absorbed by the refrigerant, let's say that's Q, the heat absorbed by the refrigerant, and the heat of the water vapors, let's say enthalpy of the water vapors, let's say HW into Mw. So we can read, I mean, we can rewrite this is the incoming enthalpy, which is equal to M1 H1. And what are the outgoing enthalpy? The outgoing enthalpy, they are, I mean, outgoing is Q, and then the plus M2 or Ma H2, and then the enthalpy of the water vapors, which is equal to plus Mw HW. So we can rearrange and then we can calculate that how much heat is absorbed. So this Q will be equal to Ma will be common. So H1 minus H2 minus Mw HW. So finally you will get this equation right after rearrangement. So this is how, by using the mass and energy balance, we can calculate the required quantities. For example, in this case, this is Q out is basically the cooling capacity of that coil. So that can also be calculated by the energy and the mass balance. Right. Another air conditioning process we call the adiabatic mixing of the airstream. As I explained, in case of the all air conditioning process, that sometimes we need to mix the return air with the fresh air for the purpose of ventilation. Let's say this is the required room where we need to have certain required condition. I mean, this is our zone basically. Technically we say that this is our zone, and you know that in all air, I mean, the out we have one of the duct which is connected with the incoming air, and then that duct is connected with the returned air as well, right? So the returned air and the incoming air, right? And there are different dampers installed along with the incoming air as well as the damper installed with the returned air. So from the zone, I mean, there are two options, whether we can mix the air with the fresh air, or we allow this air to go outside, or we stop that air, or simply we open this and we use the same air. Just like in our domestic air conditioner, that are normally either the split type, or we use the window type air conditioner. And in case of the split type, I mean, the same room air is cooled down frequently. The mixing is only take place, there is no proper arrangement of the ventilation. The mixing or the ventilation is normally achieved with the help of infiltration mean when we go outside from the room, we are opening the door, so as a result some outside air come into the room, or when we open the window, so the fresh air from the window they enter into the room. But no, but for the purpose of the cooling, we are not, I mean, adding the ventilation. The ventilation is naturally through the infiltration process. However, there are certain application where by default we need certain ventilation, especially in case of hospitals where we frequently need to add the oxygen, or the place where many gathering is there, so there are chances that the oxygen level may drop. So in those application, we need to add a constant supply of the outside air and the returned air. So how to calculate the properties of the mixed air? For that case, let's say, I mean, as seen in the figure, we have one of, let's say this section is 1, another one is 2. So one of them we can treat it as the returned air, another one the outside fresh air. So when the returned air, let me erase this. So when the returned air, let's say this is the returned air and this is the fresh air, outside air, fresh air. Right? When they're mixed together, right, then the new condition that is supplied to the zone, right, that is supplied to the zone, the condition is different than the other two conditions. So how to predict this condition? Right? Again, to predict the new condition, I mean, after mixing, again we can utilize the energy and mass balance, right? For example, you can see, first of all, we can apply the mass balance of the dry air. So whatever is the mass of the dry air at section 1 plus the mass of the dry air at section 2, that should be equal to the mass of the dry air at section 3. So this is basically the sum of Ma1 plus sum of plus Ma2, that should be equal to Ma3. So this is basically the addition. So this is the incoming dry air. So this is the outgoing dry air. Similarly, we can apply the mass balance for the water vapor. So what is the water vapors at section 1 plus water vapors at section 3? That should be equal to the water vapor at section 3. So section 1, the water vapor is omega 1 Ma1 plus the water vapor at section 2 is omega 2 into Ma2. So that should be equal to omega 3 into Ma3. So that's basically the sum of this. And similarly, for the energy balance, the enthalpy of the moisture at section 1 plus enthalpy of the moisture at section 2, that should be equal to the enthalpy of the moisture at section 3, right? And from here, as you can see, we can eliminate Ma3. This is Ma3, so we can put the value of the Ma3 here. Let's say if we put the value of Ma3 here, what will happen? Then omega 3 into the value of the Ma3 is Ma1 plus Ma2. So Ma1 plus Ma2. right? Plus Ma2. So on this side, we also have Ma1 and we also have Ma2. So the Ma1 and Ma2, they will come in one side. So we'll take common. So we'll get a ratio of the Ma1 and Ma2. We'll get a ratio of the Ma1 and Ma2, right, after simplification, right? So if you simplify, then you will get a ratio. Similarly, when you put this Ma3 here, in case of enthalpy, right, Ma3, you replace that value. So same, you can take the common because on other side you have Ma1, so you will have Ma1 on this side. So you will get this ratio. I mean, Ma1 divided by Ma3, you will have the ratio in terms of the specific humidity or in terms of the enthalpy. So this shows that this ratio shows that the mixing point always lie between the 2 points. I mean, let's say you have the fresh air at section 1 and the returned air at section 2. The mixed air will always lie in between that point. I mean, this could lie here, it could lie here. So, but it will lie on the line, a line joining the 1 and 2, right? So we can exactly figure out that point 3 if we know any one property. Let's say from if we know the masses, I mean, if we know the point 1 and point 2 and their masses, then we can figure out either H3 or we can figure out omega 3. Any of one property, if we know, then we can locate that. Let's say if we know H3, so we'll say that this is H3. So if we can locate point H3, then all of the remaining property we can figure out if we can locate the point H3. So that means the new point at section 3 always lies between the straight line connecting the two states. The next air conditioning process, it is called cooling and humidification, right? Cooling and humidification, this application is in the simple air cooler. I hope you are familiar with the air cooler. In air cooler, what is happening? The outside air is warmer. Normally in summer weather, the outside air is much hotter or warm, right? So what we do, we spray the cold water, right? We spray the cold water in the air cooler. So when the outside hot air come in contact with the cold sprayed water, then as a result, the outgoing air is humid. This is humid because you are adding the humidity. This is humid and cooler. So that means you have decreased the dry bulb temperature, but you have increased the humidity ratio, right? So that's called the cooling and humidification process. This process takes place in air cooler. So you can draw the same process on the psychrometric chart as well. As you can see, the outdoor air has a high dry bulb temperature but low humidity. So when you spray the cold water, its dry bulb temperature is decreased. So its dry bulb temperature is decreased, but you have increased the humidity ratio. I mean, this is, let's say, omega 1 or W1, this is omega 2. So how can you figure out the mass of the water vapor added? The mass of the water vapor that you have sprayed into the incoming air is basically the difference of that humidity ratio, which is equal to omega 2 minus omega 1 into mass of the dry air, right? This is again, you know that this is through the mass balance. Similarly, the amount of the heat that has, amount of the heat that has removed by the water, that can also be obtained through the energy balance. But that enthalpy is the enthalpy of the water vapor. This is again through the energy balance. I mean, H1 plus this is the mass. I mean, this is the ratio of the mass. We simplify basically. This is the energy balance. I'm not doing the same step all the time. I mean, if I just rewrite, that will be basically MaH2. This is MaH2, right? And this is the outgoing air. What is the incoming air? Energy of the incoming air. This is MaH1, right? Plus mass of the water vapors, right? And the enthalpy of the water vapors, right? So basically, we have simplified this equation and then we get the enthalpy of states 2. Right? This is enthalpy of the state 2. and we can put this value mw by aw. From here mw by aw will be equal to w2 minus w1. I mean, from here you can see we can get w2 minus w1, and this ratio can be replaced here. So if you simplify that, then you will get h1 plus w2 minus w1 into hfw. So this is how you can figure out the enthalpy of the outgoing air. Right. What about sometimes we use a word cooling and adiabatic humidification? What is the difference between cooling? I mean, when we use the word cooling and adiabatic humidification. What do you think? What is the difference between the simple cooling and humidification and when we use a word cooling and adiabatic humidification? Anyone?
Sir, this means that no heat is added from any outside or external source in the
Yeah.
process.
So technically,
So, sir, it's just increasing the moisture content.
So technically it says that the H1, this if this is adiabatic, then H1 should be equal to H2. If this is adiabatic humidification, right? When it says cooling and adiabatic humidification, this is will be a constant enthalpy line, right? H1 will be equal to H2 if it is used the word adiabatic humidification, right? All right. So let's try to solve a couple of numerical problem for this chapter. This is the first example. In this example, consider moist air is to be supplied in a zone at 30 degrees C. So let's say there is a zone. Let's say this is my office. So this is the required to supply the air at 30 degrees C. I want the temperature in my office at 30 degrees C. The steam entering in the coil is used to heat the outdoor moist air, which is at 10 degrees C and 50% relative humidity. So the outside air is much cooler, which is at 10 degrees C and 50% relative humidity, right? We need to, I mean, heat that with the help of a steam coil. It is mentioned that the steam, right? And the flow rate is also mentioned of that moisture, which is 100 kg per second of the dry air, right? The flow rate of the moisture is also mentioned, right? So that heating process take place by using a steam coil. So let's say this is a steam coil, right? Steam is entering into that. So when it come contact with that, so the temperature increases to 30 degrees C. So this is simple example of the simple heating process, right? So what is the sensible heat transfer? So in order to increase the temperature for 10 degrees C to 30 degrees C, how much is the sensible heat transfer? And how much steam flow rate is required? So you need to figure out the steam flow rate. If a saturated steam enters at 100 degrees C and condensate leaves at 80 degrees C. So when the steam enter, it is saturated steam. That means that is, let's say, G, we represented with Hg, and when it leaves, it is the condensate, which also called Hf, right? So you can draw the, first of all, let's say if you can draw the indoor condition, outdoor condition and indoor condition is very simple. You can draw on the psychometric chart, indoor condition and outdoor condition. For example, the outdoor condition, if you know any of the two properties, 10 degrees C, 50% relative humidity. So 10 degrees C and 50% relative humidity. But we know that this is simple heating. So there is a horizontal line, right? And the outdoor, I mean, the zone temperature that we have to maintain is a 30 degrees C. So this is 30 degrees C, it cuts here. So we can also locate 0.2. So simply in order to calculate the sensible heat is basically the difference of the H2 minus H1. And if you can calculate the mass of the dry air, you multiply, that will be the total sensible heat, right? H1 we can read and H2 we can read. So sensible heat transfer is simply the Ma H2 minus H1, and the mass of the dry air is already given, which is 100 kilo per second of the dry air. So this was directly the mass of the dry air. You put this value, so this is almost equal to 2050 kilowatt. So it's much higher, right? Much higher requirement for the heating, because the temperature difference is too much from 10 to 30, and mass flow rate is even very high. I mean 100 kg per second. That's a very huge mass flow rate. That's why the amount of the energy requirement is too high. I mean, if you convert this is basically the 2050 kilowatt, which is very high. The energy requirement is too high. Anyway, the next one is the how much steam is required. I mean, for the same to supply the same energy by the steam, how much steam is required? We know that the energy supplied by the steam is in the form of latent heat, because it enters as a it enters as a saturated steam and leaves as condensate. So we need to figure out at this temperature is 100. So at 100 degrees C, we need to figure out the value of Hg, and at 80 degrees C, we need to figure out the value of HF. So simply we can calculate the mass flow rate from the simple formula that for the same amount of heat, you have to divide with the Hg minus HF. So about 0.8756 kg of the steam is required in 1 second in order to attain the same amount of the heating. Right. So let's see another one. The second example. In this example, it says, consider a single duct, single zone, and constant speed air handling unit. So we study one of the all air process, which was a single duct, single zone, and constant speed air handling unit, in which 39.6 cubic per minute mixture of the outdoor air and the recirculated air, room air, which is at 31 degrees C dBT and 18.5 degrees C wet bulb temperature. It enters a cooling coil. The effective surface temperature of the coil is 4.4 degrees C. The surface area of the coil is such as would give 12.5 kilowatt of refrigeration with the given entering air state. Determine the dry bulb temperature and wet bulb temperature of the air leaving the coil, and what is the bypass factor, right? So this is the required. I hope you recall the single duct, single zone, and constant speed air handling unit, in which the first duct is, if you just recall, the first duct is the incoming air, right, and which is, I mean, the flow rate is maintained with the help of damper, right, and then that duct is connected with the returned air, right, connected with the returned air. This is also the mass flow rate is managed with the help of a damper, right, and here, right here, the mixing process may take place depending upon the amount of the damper that is opened or closed. So here, from here, we'll get the fresh air, incoming air. Here we'll get the returned air. So in the problem, it says there is a this is the mass flow rate of the mixture of the outdoor air. This is the outdoor air and the recirculated room air. I mean the air which is coming from the zone, right? That's the recirculated air. So it is mixed here, let's say, right? And its condition is mentioned. The condition of the mixture is mentioned, which is 31 degree dBT and 18.5 degree WBT. And then after that, we have the cooling coil and the heating coil. But in that case, it says it's a cooling coil. So let's say this is a cooling coil, right? So cooling coil means, let's say, maybe refrigerant can pass through that cooling coil, or maybe the chilled water can pass through that cooling coil. So after it moves, then that is supplied to the zone. I mean, here we install a blower, then blower send that air to the required zone, right? The question is that cooling coil, yeah, the surface temperature of the cooling coil is 4.4 degree. So the surface temperature of the coil is 4.4 degree C. And what is the capacity of that cooling coil? 12.5 kilowatt. So the capacity of the cooling coil is also given, that's 12.5 kilowatt. what we need to figure out that what is the temperature in the zone. I mean, after that, what is the dBT and WBT, dry bulb temperature and wet bulb temperature of the air leaving the coil. So after the coil, what is the temperature here? And also the bypass factor, because all of the air cannot come in contact with that coil. So what is the bypass factor as well? So these values you need to figure out. I think we can locate, for example, we can locate the coil, because we know that's the apparatus dew point. We can locate the coil temperature. We can also locate the mixture. I mean, here, let's say this is state 1. Right, we know the two properties. We know the dry bulb temperature and the wet bulb temperature. So we can locate one as well as the coil temperature, but we cannot locate the zone. Just we have to figure out the zone temperature, right? We have to figure out the dry bulb temperature and wet bulb temperature of the air. And then finally, we have to figure out the apparatus dew point. So that's very simple, I think, on the psychrometric chart. I mean, let's say we can mark these points. I mean, this is the first point, the point for the mixture of the outdoor air and the returned air. For that case, two properties are given. One is the dry bulb temperature, another one is the wet bulb temperature. So both temperature are given. One is value is 18.5, another one is 31 degrees C. So we can locate point 1, right? And the next we know, next point is the apparatus dew point, which is also given the effective surface temperature of the coil, which is 4 degrees C, right? So that's also called the ADP. So that's now the temperature or the condition in the zone will always lie in between that. It is lie, but we don't know that point. That this point 2 is lying where? It could be, I mean, center of here, it could be here, it could be here, but it will lie on that line. So that means we need to figure out any of the two property of any one property. If we know any one property, we can locate point 2, and then we can figure out the dry bulb temperature and wet bulb temperature, right? So how can we figure out? I mean, we know that from point 1, since we have located, so we can read all of the property at point 1. All of the properties mean what is H1, right? H1 we can read. We can also read W1. Similarly, we can also read the specific volume, right? Specific volume we can read. Similarly, at point 4, we can read all of the unknown property. For example, H4 we can read a W4, right? So W4, H4 and W4, right? And then since we know the specific volume and the volume of the mixture is also given, which is 39.6 cubic meter per minute, and the unit for the specific volume is cubic meter of the moisture per kg of the dry air. So if we divide these two, we can calculate the mass of the dry air. So here you can calculate the mass of the dry air. And we also know the cooling capacity. I mean, what is the cooling capacity of that coil? Cooling capacity means the heat removed by this coil. So we know that the heat removed by this coil is from 1 to 2, right? 1 to 2 is the cooling capacity, which is equal to MAH1 minus H2. So the cooling capacity is already given to us, and the mass of the dry air we have already calculated, right? And H1 we have already located. So we can figure out H2. So that is our requirement. I mean, if we can figure out any of one of the property, we can locate that point. So from here, if you put these values, like you rearrange and you put the value of the Q, which is equal to 12.5 kilowatt, right? You can convert in, you can divide with the mass and you can multiply with the 60. That will be in the units of kilojoule per minute, because the mass flow rate is in kilojoule per minute. So you should have the same unit. So then you simplify that, you will get H1 minus H2 as kilojoule per kg of the dry air. H1 is already known to you. Then you can calculate H2. So the H2 will be equal to 35.61 kilojoule per kg of the dry air. So once you figure out that, on the line between 1 to 4, you can locate point 2. Now the other one, for example, let's say what will be the bypass factor? Bypass factor mean the actual process take place between 1 and 2, right? The actual process take place 1 and 2. So how much is the bypass? This is the bypass, right? So bypass out of total. So bypass factor mean H2 minus H4, right? This is the bypass because actual process take place between 1 and 2. So this is bypass H2 minus H4. What is the total? H1 minus H4 divided by H1 minus H4. So this is the bypass factor. So we can easily figure out because we know we just calculated the value of H2, right? H1 is already known to us. H4 is also already known to us. So simply we can calculate the bypass factor. Right? The bypass factor can be calculated both from the humidity ratio as well as from the enthalpy. It doesn't matter. Right? And the W2, yep.
Excuse me, sir, I had a question.
Yep.
Sir, the ADP, will it always be located at the 100% specific humidity line?
We assume that that temperature is on the saturated point because in case of cooling process, when the outside air come in contact with the surface, right, it condensate. That means condensate mean the temperature of the surface is below than the dew point temperature of the moist air. That's why the ADP or the effective dew point temperature is always taken on the 100% relative humidity. So from here, as you can see, we can easily calculate the bypass factor, right? So bypass factor is calculated. Even you can read W2 because you have located point 2, or even by equating this, you can read W2. It's up to you, right? So you can, calculate the bypass factor. So the value of the bypass factor is about 0.5146. That means about 51% of the air is bypass. So only 49% air will come in contact with that cooling coil, right? Okay, so let's try to calculate another example. This is example 3. So in this example, let's say consider a room is to be maintained at 22 degrees C and 55% relative humidity. So this is the requirement that you have to maintain this condition, air conditioning through air conditioning process, whereas the outside air is saturated air at 3 degrees C is first heated and then water at 10 degrees C is sprayed to get the required humidity, right? For this process, calculate the required mass of the sprayed water per cubic meter of the air. So you need to calculate the mass of the sprayed water per cubic meter of the air, and also the temperature to which the air must be heated. So if you try to draw the process, let me draw that process. This process says that there is a room. Let's say this is the room. So in that room, you need to have the temperature equal to 22 degrees C and 55% relative humidity. Let's say this is a comfort zone. So you need to maintain that comfort zone. However, the outside air is saturated air, right? That's a saturated air at 3 degrees. That's much cooler, right? So that means that's at 3 degrees C. So what you have to do, you have to first heat, right? You have to first heat in a heater, and then water at 10 degrees C is sprayed to get this condition. So from 2 to 3, the water is sprayed and the temperature of that water is 10 degrees C, and then you can get that condition. The question is, what is the required mass of the sprayed water per cubic meter of the air? So how much mass of water is sprayed, right? And then the temperature to which air must be heated. From 1 to 2, in other words, what is the value of T2? The temperature to which air must be heated. So this is how you have to figure out. I think you can easily locate the first point because this is a saturated where the phi is 100% and the temperature is given 3 degrees C, and you can locate the room condition, right? Whereas the point 2 is difficult to maintain. This is the 3 is basically the room condition, Right, this is the 3 mean the same condition as the room. So 3 and 1 can easily be located, but we cannot locate point 2. So let's try to draw on the psychometric chart. On psychometric chart, as you can see, the condition 1 mean the air is saturated. So on 100% relative humidity and the temperature is 3 degrees C. So that can be easily located. Whereas the room condition, which is 3, we know the temperature is 22 and the relative humidity is 55%. So relative humidity is 55%, is 55%, and that temperature is equal to 22 degrees C, right? So it can easily be located, but the point 2 is not possible to locate because from 1 to 2 is simple heating. So it is a horizontal line. So it is a heating, but we don't know the point 2 where it is located. So this is basically you have to figure out point 2 and also the required mass of the water vapor. This is very easy to calculate, I think. Mass of the water, I mean, just by the mass balance, you know that this is the difference of the omega. I mean, this is, let's say, omega 3, this is omega 2. So that means actually it should be omega 3 minus omega 2 into mass of the dry air. And then how can we get the temperature? I think we can apply the energy balance between 2 and 3. I mean, if you apply the energy balance, you can get the temperature as well. So let try to solve this problem. So at point 3, we are given two conditions. We can locate that point. So simply we can read the value of the omega 3. Right. Similarly, at point 1, we know that this is 100% relative and 3 degrees C. So we can read omega 1 or the W1, and W1 is equal to W2 because this is a horizontal line. This is simple heater, the simple heating process. So W1 is equal to W2. So the difference of the enthalpy, I mean the W3 minus W2, or because W2 is equal to W1, so W3 minus W1 is the difference of the omega. And then since we need to figure out the mass of the water vapors per cubic meter of the dry air, so that means we have to figure out the volume of the dry air. So we can figure out the volume of the dry air from the ideal gas equation, RAT into PA. So we are given the outside air temperature, I mean the required air temperature is 22. We know the value of the gas constant for the dry air, and then we have to figure out the pressure, I mean vapor pressure. Then we can calculate the value of the, even we don't need to apply this formula. I mean, we can directly read here from this chart. You know that there are the lines for the specific volume line. We can directly read this value from that chart. So this value will come out to be 0.847. So you just divide with that. Then you will get the, if you divide with that, then you will get the mass of the water vapors per cubic meter of the dry air, because this was the requirement that you have to figure out the mass of the water vapor per cubic meter of the moist air. And then the second is the temperature to which the air must be heated. Now to get that, I mean, what is the temperature here? I mean, the second point, for this case, you have to apply the energy balance between the 2 and 3, right? Between 2 and 3, if you apply the energy balance between 2 and 3, that means what is the energy at inlet? I mean, at 2, this is also the energy entering of the water vapors, that must be equal to the energy at point 3, right? So that means MA H1 plus MW HW, that should be equal to MA H3, right? So simple energy balance, right? So if you apply the energy balance between 2 and 3, which is equal to H2 plus MW HW is equal to H3. I mean, H2 means the enthalpy of the moist air, right? Similarly, this is enthalpy of the moist air. This is enthalpy of the water vapors. And we know that the mass of the water vapors, this mass of the water vapors is omega 3 minus omega 1 into mass of the dry air, right? Whereas the enthalpy of the dry air, whereas, yes,
Excuse me, sir. Sir,
yeah,
could you repeat why we use the formula again?
which formula?
Sir, R naught T3 over P.
This one?
Yes, sir, this formula.
Okay. If you read the statement, basically, if you just need to calculate the mass of the water vapors, I mean, if you just need to calculate what is the mass of the water vapors, so we know that mass of the water vapors is simply the difference of the omega value. I mean, omega 3 minus omega 1 into mass of the dry air, right? You know that we form to get the mass of the water vapor. This will give kg of the water vapors. But in that case, it says calculate the mass of the water vapors per cubic meter of the air. Right. So for that case, we need to figure out the volume first. So specific volume we can directly read from. We don't need to apply that formula empirical relation, since we can also get the same value by using the psychometric chart. So you just read the value of the specific volume. You know the units of the specific volume. This is 0.847 cubic meter of the moist air per kg of the dry air, right? And what are the units of this one? Kg of water per kg of the dry air. To get the kg of the water vapors per cubic meter of the dry air, so this will be cancelled out with this one if you divide that, right? So the remaining will be kg of the water vapors per cubic meter of the moist air. You got the point?
Yes, sir, thank you.
Okay, so then to get the temperature at point 2, you have to apply the energy balance between 2 and 3. So this is simple energy balance. You know that the enthalpy of the water vapors, HW, we can figure out from the empirical relation as well as we can also get from the steam table. If you recall the previous lecture, that the enthalpy of the water vapors, both we can get from this equation if we know the temperature, right? And also from the steam table as well. So since the water was supplied at 10 degrees C in the statement, so we can get the enthalpy of the water vapors, right? And the mass of water vapors, we know that this is the difference of the relative humidity, right? So then finally we can through the energy balance, we can get that value of the enthalpy H2, which is equal to this value. So this enthalpy we can locate here, that enthalpy value is 36 kilojoule. So we can locate that point 2. So then when we locate that point 2, we can read that temperature, which is approximately equal to 27 degrees C. Okay, let's try to solve the last problem. This problem says uh, this is a design problem. Let's say you are required to design an air conditioning plant for the LH2 of the FME. Let's say in our classroom where we have the seating capacity of 60 students, right? In our FME classroom, let's say I'm giving you that task, that design an air conditioning plant. Designing means the capacity of that plant. What should be the, let's say, air conditioner that need to be installed in our FME room, LH2, where the 60 students, they are sitting here. Let's say the weather condition is the current situation nowadays. I mean, that's the winter season, and assume that for a particular day, let's say today, the outdoor condition are measured with the help of a sling thermometer. You know that the sling thermometer give you two temperature, the dry bulb temperature and the wet bulb temperature. Now it says that the dry bulb temperature is 12 degrees C and the wet bulb temperature is 10 degrees C, and the pressure is 1 atmospheric pressure. The required conditions in the classroom are 20 degrees C and 60% relative humidity. So during the winter season, we want this condition in the classroom where the 60 students are sitting. And for the air circulation, we must need, according to ASHRAE standard, in order to have the proper circulation, the quantity should be 0.3 cubic meter per minute per person from the ASHRAE handbook, right? The required conditions in the classrooms are achieved by first heating and then adiabatic humidification. So, I mean, that's the adiabatic humidification and first heating and then adiabatic humidification. So you need to design the air conditioning plant. So the required, I mean, air conditioning plant mean, design of the air conditioning plant mean what is the heating capacity of the coil, and surface temperature of the coil. If the bypass factor is of the coil is 0.4, and what is the capacity of the humidifier, right? This is these things you have to calculate. So if I just simplify the problem, this is LH2, right? Where we want nowadays 20 degrees C inside that classroom, LH2, and 60% relative humidity, right? And nowadays, let's say today, the outside air is, let's say at 0.1, outside air is at 12 degrees C with the help of the sling thermometer, and 10 degrees C dry bulb temperature, wet bulb temperature. One is dry bulb, another one is the wet bulb temperature. And then we can have the required condition for 60 people, 60%, I mean 60%, let's say students, and for 1% the air circulation rate is 0.3 cubic meter per minute, right? I mean that circulation rate is also given, and this condition can be accomplished by first heating, and then adiabatic humidification, as I showed you the adiabatic humidifier, right? Adiabatic humidifier, I mean in which the spray is there, is kind of a spray, but this is fully insulated, right? And then you can achieve that condition. So let's say heating process from 1 to 2, and then 2 to 3 is the adiabatic humidification. So for that case, we need to figure out that what is the capacity of that coil, heating coil, as well as capacity of the humidifier, right? We need to figure out the capacity of the humidifier as well as the capacity of the cooling coil. So let's try to solve. First of all, we can locate the situation. We know the outdoor condition with the help of the sling thermometer, which was 12 degrees C and 14 degree, 12 degrees C. It was, what was the condition? It was 12 degree dry bulb temperature and 10 degree wet bulb temperature. So 12 degrees the dry bulb temperature and 10 degrees the wet bulb temperature. We also know that what condition we want to achieve in the room, that's 60% relative humidity and 20 degrees C. But we don't know the condition between 1 to 2, right? We don't know the condition at 2. And also this heating is the surface temperature, we don't know that what is the surface temperature of that coil, right? Apparatus dew, we also call the apparatus dew point, right? So basically, I mean the surface temperature of the coil will be obviously is larger than the 0.2. I mean if you see that, I mean surface temperature of the coil is larger than the temperature at 2, right? Because all of the heat cannot be transferred from, let's say that surface temperature, let's say is point is 4, right? So the temperature 2 cannot be greater than temperature 4, right? So and then we have the surface 3. So in that case, if we say the cooling capacity of the coil, that mathematically will be equal to H2 minus H1. I mean the cooling capacity of the coil is basically H2 minus H1, and the capacity of the humidifier is basically, I mean we are adding the moisture content, that will be basically the difference of the humidity ratio, which is W3 minus W1 or minus W2, because W1 is equal to W2. So we can take either W1 or we can take W2. Both are equal. So that will be basically the capacity of the humidifier. So basically what we have to do, we have to locate point 2, right? And we can locate point 2 if we know any of the property. I think we can directly locate point 2. Why we can locate point 2? Because it is mentioned that we are using a adiabatic humidifier. When we use the word adiabatic humidifier, that means H3 is equal to H2, right? So H3 is also already known to us because 0.3 we have already located on the graph. So 0.3 means 60% relative humidity and 20 degrees C. So when we know 0.3, that means we also know H3, right? So H3 is equal to H2. So that means when we know H2, we can locate point H2. So simply we have to read the enthalpy from the table, and then we can, I mean, we can draw all of the point, and then I mean, we know the mass of the dry air. We can simply know that was for the per person, right? We can read the specific volume here, right? Either from here or here. We can read the specific volume for the 1%, and we multiply with the 60%. So this much mass flow rate is required. I mean, this is the for the per person, and this is the specific volume. So if you divide that, you will get the mass flow rate of the dry air per minute, and this is for the 60%, right? And then obviously we can simplify the heating capacity. Heating capacity is basically H2 minus H1 multiplied by the mass flow rate of the dry air. So simply we can read the H1 as well as H2, which is equal to H3. So this is the about 4.77 kilowatt of the is the cooling heating capacity of that coil. And next we have to figure out the that bypass factor as well. But we can read bypass factor if we know the surface temperature of the cooling coil. I think bypass factor was given, that was 0.4. That means the 40% of the air is bypass. So bypass, I mean bypass is this much, 2 to 3. Actual process take place from 1 to 2, and the bypass is from 2 to 3. So bypass divided by the total one. So H4 minus H2 divided by H4 minus H1. That will be the bypass factor. So bypass factor is given 0.4. We need to calculate the surface temperature of the heating coil, which is the T4. So from here we can get value of the T4, which is equal to 32.8 degrees C. What about the capacity of the humidifier? Capacity of the humidifier is basically the difference of the humidity ratio, which is H3 minus H2. So the capacity of the humidifier is basically W3, I mean that W3 minus W1 into MA. Actually, it is divided with 1000, and with the 60 persons, then you can have kg per hour, right? Because the unit for the omega is, I mean, as you can say, the unit for the omega is milligram of the water vapors per kg. So if you divide that, that will be equal to kg of the water vapors per kg of the dry air. So if you simplify that, you will get about 2.379 kg of the water vapors in 1 hour. So this is the requirement for the capacity for the humidifier, right? So that's the end of the class. Please practice these problem, about 5 problem for the practice in chapter 3, and then there will be next quiz, quiz number 5 from chapter 3, that will be in coming Monday, December 21st at 6 p.m. That will be again online using the MS Team. If you have any question, you can ask me.
Excuse me, sir, will it just be a quiz?
Yeah, just a quiz.
Okay, and sir, just one more question, sir.